Welcome students. Myself Dinesh, working as assistant professor in physics. Dear students, in this session I am going to explain interference filters. Dear students, in this session we will describe how the filters operates and when filters should be used. Let us see one by one in detail. See here, an interference filter is an optical system that will transmit a very narrow range of wavelengths and thus provides a monochromatic beam of light. It means a small amount of incident light are reflected at the interface between two materials of different refractive indices. Thickness of the material will alter the constructive or destructive interference patterns, increasing or decreasing certain wavelengths. Optical filters can be created that interfere with the normal transmission of light. Let us see optical filters. Here optical filters are classified into two types. First one, interference filters. Here dichroic, dielectric, reflective filters which reflect the unwanted wavelengths. Second one is absorptive filters, the color glass filters which absorb the unwanted wavelengths. Dear students, now we shall discuss about the interference filters in detail. How the interference filters are constructed and how it works. Let us see. Here when a parallel beam of white light is incident normally on a pair of plain parallel plates silvered on their inner surfaces, just as an fabric parrot athlon. Here interference results for all the component wavelengths of incident light. The maxima of different orders are formed in the transmitted light only for those wavelengths which satisfies the relation. We know that for normal incidence it is given by the formula 2 mu t equals n lambda. Here T is the separation of the plate, where mu is the refractive index of the medium between the plates, and n is the order of maxima, that is n equals 1, 2, 3 and so on. When T is reduced, the maxima becomes widely spaced. For an air film, the refractive index is equal to 1 when T is kept between 2 into 10 raised to minus 7 meter and 6 into 10 raised to minus 7 meter. It is easily seen that the film transmits only one maximum in the visible region. For example, if t equals 5 into 10 to the power of minus 7 meter, nearly equal to 500 nanometer, the transmitted wavelengths giving maxima are given by lambda equals nearly 1000 nanometer or 500 nanometer and 333.3 nanometer and so on. Out of these, only wavelength 500 nanometer lies in the visible region. In this way, with visible incident light, it is possible to filter a particular wavelength. That means, or a narrow band of wavelengths. With such a structure, that is why such a structure, example, a pair of parallel glass plates silvered at inner surfaces. That structure is known as the interference filters. Let us see how it is prepared and how it works. Interference filters using the principle can be prepared by modern vacuum deposition technique. A thin metallic film of aluminum or silver is deposited on substrate, usually a glass plate, by vacuum deposition techniques. Then a thin layer of some dielectric material such as cryolite is deposited over this. This dielectric is in turn coated with another similar metallic film. To protect this thin film structure from any damage, another glass plate is placed over it. This arrangement forms a fabric-parrot structure between two glass plates. By varying the thickness of the dielectric, any particular wavelength may be filtered. Actually, speaking, a narrow band of wavelengths sharply peaked about one wavelength may be filtered as in interference filter. The sharpness of the transmitted spectrum is determined by the reflectivity of the metallic structure. The layer is the reflectivity, the narrower is the transmitted spectrum. However, it is not possible to increase the thickness of the metallic films indefinitely, since this would in turn reduce the intensity of the transmitted light. To overcome this difficulty, the metallic films are replaced by all dielectric structure. In all dielectric structure interference filter, a lambda by 4 thick film of titanium oxide whose refractive index is nearly 2.8 is deposited on a glass substrate. Then a thin film of dielectric material with lower refractive index such as cryolite is deposited on the titanium oxide. On this, a lambda by 4 thick film of dielectric material of higher refractive index is deposited again. To transmit a narrow band, higher reflectivity is essential. This is achieved by using multi-layer structure of higher and lower refractive indices. Such Such interference filters are capable of transmitting a band of wavelengths as small as 1.1 nanometer or even less, with peak at any wavelength within the visible region. Nowadays, metallic films are not used. Instead, the dielectric films are used. Let us see the interference filters advantages. They can be used as reflectors in 2 and 3 color analysis. They usually do not themselves produce fluorescence. Interference filters, they do not themselves produce fluorescence. They are available in short pause versions. They are always available in short pause versions. They are excellent as primary barrier filters. These are the advantages of interference filters. Thank you.